Okay, so today we will start the statistical thermodynamics. So here the statistical thermodynamics is divided into two parts in your syllabus. The statistical thermodynamics is divided into two parts. The first one is introduction to statistical thermodynamics. So today we will discuss about the introduction part. So, so here in the introduction part, you, uh, you will be introduced to an alternative approach to understand the thermodynamic properties of a system. Whatever you have studied, the different thermodynamic properties, starting from your intermediate level, graduation level, so it is an alternative approach to understand the thermodynamic properties of a system. It is based on the application of statistics for a large collection of microscopic systems like atoms and molecules. In fact, it provides the link between the microscopic perspective of matter and the macroscopic, that is for bulk properties. So the statistical thermodynamics will provide a link between the microscopic properties, perspective of matter means if we will deal the different properties in atomic or molecular level, and for macroscopic or bulk, whatever you have studied from your intermediate or graduation level, so that is applicable for macroscopic level. So here the statistical thermodynamics provide a link between both the microscopic and macroscopic or bulk properties, that is the observable properties. This approach can be used to calculate bulk thermodynamic properties such as internal energy, enthalpy, entropy, Gibbs energy of the system, and structural and spectroscopic data of the microscopic species constituting the thermodynamic system. So that means what you have studied the different thermodynamic properties previously, like internal energy, enthalpy, entropy, Gibbs energy, all those things are macroscopic properties, because so these are deals with bulk of the matter. So these are the properties which deals with bulk of the matter, and these property, and here the statistical thermodynamics will use to calculate the bulk thermodynamic properties using spectroscopic data. Spectroscopic data is obtained from the atomic or molecular level. Now, in a way, the statistical thermodynamics can be considered as a mathematical tool that bridges the gap between the properties of the individual atom or molecules, that is in the microscopic level in a system, and the macroscopic thermodynamic properties, that is for bulk of the matter. Alternatively, the statistical thermodynamics can be visualized as a vehicle that serves to provide the means to extend the properties of individual atoms or individual molecules to a large collection of them. So if you will deal with the properties of individual atoms or molecules, so these are, so that properties, those properties will be the microscopic properties, because here we are considering for individual the properties of individual atoms or molecules. So that is the microscopic properties. And to a large collection of atom means, so if you take a bulk of atom and if you deal with the thermodynamic properties, so that is in the macroscopic level. So that means if you consider atomic or molecular level, that is microscopic level, the science deals with that, that is known as quantum mechanics. So this is for atomic or molecular level, and for bulk level, that is called classical thermodynamics. And here the statistical thermodynamics will act as a bridge between quantum mechanics and classical thermodynamics. So that means that will provide a link between quantum mechanics and classical thermodynamics. So the first one is classical versus statistical thermodynamics. So here, in order to compare the classical thermodynamics and statistical thermodynamics, so we should consider different type of examples. The classical thermodynamics uses the data based on the bulk properties of the matter, Already we have discussed that. So the classical thermodynamics deals with the bulk property. Bulk property means the property which deals with large number of species. So bulk properties of matter. For example, if we measure the density of any matter, pressure, heat capacity, internal energy, enthalpy, entropy, all these things are bulk properties of matter. Whereas the statistical thermodynamics uses the molecular properties like bond length, quantized energies, vibrational frequencies, etc. So these properties will be calculated, or these properties will be measured in atomic or molecular level for any type of matter. For example, the experimental value of enthalpy of formation of water, enthalpy of formation of water is minus 241.8 kilojoule per mole at 25 degrees Celsius and 1 atmospheric pressure. Now it refers to the enthalpy changes associated with formation of 1 mole of water vapor from its constituent elements in their standard state under standard condition. Because we know that enthalpy of formation of any compound means it is the enthalpy change when 1 mole of that compound will be formed from its constituent elements. So here enthalpy of formation of water means it is the enthalpy change when 1 mole of water in gaseous state, that means H2OG, will be formed from the constituent elements hydrogen and oxygen. And here the enthalpy of formation of water is minus 241.8 kilojoule per mole. That means when 1 mole of water will be formed, when 1 mole of water in the gaseous state, that will be formed from its constituent elements, that is H2 gas and O2 gas, then 241.8 kilojoule amount of energy will be released. So that's why it is a negative sign is there, because here the energy will be released. And classically speaking, it has nothing to do with the microscopic nature of the species involved and what determines the observed values. So here the enthalpy of formation of water is minus 241.8 kilojoule per mole. So when you will measure the enthalpy of formation of water experimentally, so it do not interfere with, or it do not involved with the microscopic nature of the water molecules, or what is the bond length or bond angle, what is the structure of the water molecule, etc. So that means, so it has nothing to do with the microscopic nature of the species involved, what determines the observed value. On the other hand, the statistical thermodynamics deals with the individual atoms or molecules, determines the observed value. In conclusion, we say that the classical thermodynamics ignores the molecular complexity. So the classical thermodynamics only consider for bulk of species, but in quantum mechanics that deals with the nature of the atomic or molecular level, whereas the statistical thermodynamics deals primarily with the quantum mechanical nature of the atom and molecules. It's stated above, statistical thermodynamics represent a probabilistic approach to study the thermodynamic systems. Therefore, basic understanding of probability and related concept is must to learn the statistical approach of the thermodynamics. So that means the statistical thermodynamics deals with both the microscopic and macroscopic properties of the matter. Now, before going to the details of the statistical thermodynamics, in this first unit, we'll discuss some very simple statistical methods. The first one is basic probability theory. So in this theory, what we will discuss, if an experiment can be more than one outcome, then the probability refers to the chance of getting a particular or desired outcome. Suppose if you do one experiment multiple times, and for multiple times you are getting different types of result or different types of outcomes, the probability means that is chances to get a particular result. So it is the probability means it is the chance to get a particular result. The most common example using the probability is touching a coin. Touching a coin. A coin has two faces. We know that a coin has two faces, head and tail. In an experiment involving tossing an unbiased coin, so the outcome can be either a head or a tail. So the head and tail refers to as possible events or possible outcomes of tossing a coin. So if we toss a coin, so the outcome will be either head or a tail. Now, if you will toss the coin once, then the probability of getting head is mathematically written as probability of getting head, or that may be written as pH or pH like this. So that is 1 by 2 half. So the probability of getting a head for tossing a coin once is 1 by 2. Thus, there is 50% chance of getting head and 50% chance of getting a tail in a throw of the coin. The total probability of all the events in an experiment always equals to 1. That means probability of getting head or plus probability of getting tail will become 1. So now we'll extend this idea to a large number of experiments. For example, if two coins are tossed simultaneously, then the possible outcomes will be, so this is the possibility of first coin. So here the two coins will be tossed simultaneously. That means simultaneously you have to toss two coins. So the different possibilities are that there will be a chance of two heads. There will be a chance of first coin will be head and second will be tail. And another chance is first will be tail, second will be head. And another chance will be two coins will be tail. So the collection of all the possible outcomes in an experiment is known as sample space. Again, I am repeating, the collection of all possible outcomes in an experiment, the collection of all possible outcomes in an experiment is known as the sample space. So here this is the sample space if two coins are tossed simultaneously. An event refers to an outcome or collection of outcomes in the sample space, or may include null set as well as a set of all possible outcomes. For example, the sample space for tossing two coins has 4 outcomes or 4 events. So these are the sample space for tossing two coins. So if you toss two coins, so the sample space has 4 results or 4 outcomes or 4 events, and the 4 results are HH, TT, HT or TH. These constitute the sample space for the experiment. Now let us take an example of traveling from city A to city C via city B. If there are if there are X ways of reaching city B from city A and Y ways going from city B to city C, then the total number of ways one can go from city A to city C will be XY. So that means here you have to travel from city A to C and again from C to B. So if the number of ways for traveling A to C is X and number of ways for traveling C to B is Y, then the total number of ways one can go from city A to C will be XY. Therefore, the sample space for the event will consist all the XY element. You may note that here the probability of an event may consist of a series of actions, so that the sample space consists of all possible outcomes. If the sample space has n mutually exclusive event and an event of interest is A occurs I times, again I am repeating, if the sample space are n mutually exclusive event, that means in the sample space if there will be n mutually exclusive events and the events of interest A occur I times. So you will consider a particular event A that will occur I times, and total number of events in the sample space will be n, and for a particular event A will occur I times, then the probability of getting that particular event A, that is PA, equals to I divided by n. Therefore, the probability of event getting one head and one tail will be 2 by 4, because one head and one tail, that means HT, one head and one tail will be 2 by 4. So why 2 by 4? Because total number of events will be 4, one head and one tail will appear two times. So the probability of getting one head and one tail will be 2 by 4, that is equals to half. In this case, the event is getting one head and one tail and include two elements of the sample space. It refers to the following sets, that may be the first one may be head and the second one will be tail, or the other possibilities, first one will be tail and the second one will be head. That means HT and TH of the sample space. So this example refers to the probabilities associated with single experiment throwing two coins. So this is the probability associated with for a single experiment of throwing two coins. So here we will consider one example. Consider an experiment involving tossing of a coin 4 times. Consider an experiment involving tossing of a coin for 4 times. So that means you have to toss the coin for 4 times and calculate the probability getting 2 heads in the experiment. So here you have to calculate the probability for getting 2 heads. In order to calculate the probability of getting 2 heads, first you have to write the sample space. In this case, we have a coin that to be tossed 4 times. In every toss, we have two possibilities outcomes, that may be one head or tail. We can write down all the possible outcomes. All the possible outcomes means you have to write down the sample space. First, the outcome number 1. The outcome number 1 will be for toss 1, that may be H, toss 2 H, toss third toss H, fourth toss H. And the second outcome may be first toss T and the remaining toss H. The third outcome will be first toss H, third and fourth toss H, only the second toss will be T. And similarly, you will find 16 different types of outcomes. So there are total 16 possible outcomes in the experiment tossing a coin 4 times. That is, the sample space has 16 results, or the sample space has 16 outcomes. Out of the 16 possible outcomes, 11 of our requirement, 11 outcomes meet our requirement. That means having at least 2 heads. So here so these are the 16 possible outcomes for tossing a single coin 4 times. Out of the 16 possible outcomes, our requirement is to get head twice. So if we count, there will be 11 meet of our 11 outcomes meet our requirement having at least 2 heads. Therefore, the probability of getting 2 heads after tossing a coin 4 times will be 11 by 16. That is the number of desired outcomes divided by total number of possible outcomes. Similarly, when you roll an unloaded dice, so we know that the dice has 6 faces. So that is the one in which the chance of any one of the 6 faces to be on the top face is the same as that of other face. So the probability that we get Number 6 on the top face is 1 by 6 because the dice has 6 faces. The first each face contribute 1, 2, 3, 4, 5, 6. Out of the 6 numbers, each face you will so in one face you will find one dot, in the another face you will find two dots, in the another face you will find three dots, and likely in the last face you will find six dots. And here if we will roll that dice, and our requirement, we have to calculate the possibility of number 6, the possibility to get number 6. Here the probability to get number 6 is 1 by 6 because the sample space contains 6 number of results, and out of the 6 number of results, if you want to get the number 6, then the probability will be 1 by 6 of its 6 possible outcomes. Similarly, the numbers from 1 to 5 will have the same probability, and if you add all the probabilities, that will become 1. So this is the probability of getting a 6, this is the probability of getting a 5, this is the probability of getting a 4, probability of getting 3, probability of getting 2, probability of getting 1. So if you add all the probabilities, that will become 1. Now, so this is so here we are discussing very simple cases. Now we'll consider a slightly more complex cases of rolling a pair of unloaded dice. So in the previous case, we have to roll a single dice, but here it is the case of rolling a pair of dice. Then only one outcome in which get the sum of the numbers on the top face will be equal to 2. That means if both the dice show 1, then the event will be identified as throws of 2, because here we are rolling a pair of dice. And if we want to find the event is we want to find the result as the sum of the numbers on the top face will be equals to 2, then the probabilities will be 1. So we both the dice show 1. So when both the dice show 1, such event is identified as throws a 2. Similarly, there are only two possibilities for throws a 3. The two possibilities are, so the first dice will be 2 and the second dice will be 1, and the other possibility will be the first dice will be 1 and the second dice will be 2. All the possibilities in the rolling of a pair of dice are the compiled below. So here outcome as a throw of 2 will come once, outcome as a throw of 3 will come twice, outcome as a throw of 4 will come thrice, outcome as a throw of 5 will come 4 times, outcome as a throw of 6 will come 5 times, number of ways, 5 number of ways, outcome to come 7 will be 6 number of ways, outcome to get a throw of 8 will be 5 number of ways, outcome to get a throw of 9 will be 4 number of ways, and similarly outcome to get a throw of 12 will be 1 number of ways. So the total number of ways will become 36. So the sample space for rolling a pair of dice has a total 36 results or 36 outcomes. You may note that in the above experiment, throwing a 7 is the most probable event. So here you can see that throwing a 7 is the most probable event because the one that can be accomplished in the greater number of ways, since it has occurred 6 possible ways, it has the probabilities 6 by 36, that is 1 by 6. You may also note that 6 ways of throws a 7 are. What are the different 6 ways? First will be 1 and the second will be 6. First will be 2, second will be 5. First will be 3, second will be 4. First will be 4, second will be 3. First will be 5, second will be 2. First will be 6, second will be 1. So all these are these are the 6 ways of throws a 7. Now, it is important to state that The random or randomized variables or quantities are those variables whose value can change throughout the course of the experiment or series of events. In the above example, the sides of the coin, in the above example, the sides of the coin, the number on the top face of the dice are the variables that can change the outcome of the experiment. The variable can be discrete variable, that is, the ones that can have countable number of values. For example, a coin has only two sides, so it has only two variables. Whereas a dice has six sides, so it has six variables. In the event of picking one student from the 60 students has 60 variables. It is important to note that the number of outcomes may be astronomical. However, as long as the possible outcomes are countable, it will remain discrete. In case of discrete variables, the sample space is represented as a collection of all the variables. For example, the sample space of experiments involving throwing a pair of dice will be, so this is the symbol of sample space 1, 2, 3, 4, 5, 6. On the other hand, we can have continuous variable that have any value in the given range value, say a real number between 0 to 1. An example of continuous variable contrasting to the discrete variable, a continuous variable. So in the previous section we have discussed the discrete variable, that means particular results will come, but in continuous variable what will happening in continuous variable has uncountable set of possible outcomes. Temperature is another example of continuous variable, as the system changes can anywhere from 0 Kelvin onwards. Yet another example could be distance traveled by different peoples with a given time interval. So this is another example of continuous variable. So in case of continuous variable, the sample space is represented by a stating state of limit in which the variable varies. That is, the variable x may have any values ranges from a to b. That means a is less than equals to x less than equals to b. For example, the outcome variables x can have any values from 1 to 100. It will be represented as. So again I am repeating, the outcome variables x can have any values from 1 to 100. Then how can you represent that? So just you have to write, so the outcome value of x may have any values, the x may have any values from 1 to 10, so that can be represented as 1 less than equals to x less than equals to 100. So it is pertinent to point out that the chemical synthesis where we are interesting the observables are random and fluctuating in nature. For example, the instantaneous vapor pressure of a liquid in equilibrium with the vapor pressure, because the vapor pressure, when we do any type of chemical uh, experiments, so the vapor pressure continuously fluctuate around an average value. Similarly, the energy of the system at constant temperature or the volume of the system at constant pressure keep on fluctuating around one average value. However, the outcome of the measurement may differ from the average value and cannot be predicted. Therefore, we need some kind of probability distribution or to describe the behavior of the random variables. So here we will apply the permutation and combinations to find the probability distribution of a particular variables from the sample space of experiments. To calculate the probability of an event, we need to count the total number of events. In order to calculate the probability, we have to, that already we have discussed. In order to calculate the probability, we have to find, find the total number of events. So this is an easy exercise in situation when the when there will be a small number of events. However, The exercise become increasingly difficult when the number of events will be very large. So when there will be small number of events, then you can easily count that one. The number of probability we can count. But when the number of events will be very large, that means if you consider one example, simultaneously tossing of 100 coins or rolling of 20 dice, a much easier way to calculate the total number of outcome of an experiment is based on fundamental computing principle, fundamental counting principle. So here in the previous section we have discussed about tossing of a single coin, tossing of a single coin 4 times, rolling of a dice, rolling of 2 dices, etc. But here, if we will go for any type of experiment where tossing of 100 coins will be there or rolling of 20 dices will be there, then there will be a large, then there, then the number of events will be large in this type of case. So, in this type of case, a much easier way to calculate the total number of outcomes of an experiment is based on fundamental counting principle. In order to calculate the total number of experiment, we have to uh, uh, consider the fundamental counting principle. Now, according to the fundamental counting principle, if there are n1 ways of doing the first thing and n2 way of doing the second thing, again I am repeating, if there are n1 ways of doing the first thing, n2 number of ways of doing the second thing, and n3 number of ways of doing the third thing, and so on, then the total number of possible outcomes will be equals to n1 whole into n2 into n3 and so on. So let us calculate the total number of outcomes for rolling a pair of dice by using fundamental counting principle. So if so roll simultaneously 2 dice, so in this case, the number of outcomes for rolling of a pair of dice by using fundamental counting principle. What is that principle? So this principle deals with this one, and here we are taking one example. For rolling of the first dice, there are 6 possible outcomes. Similarly, for rolling of the second dice, 6 possible outcomes. Then the total number of possible outcomes will be equal to 6 into 6, that is 36. Similarly, if you roll 3 dice, then the total number of outcomes will be 6 into 6 into 6, that is 216 or 6 to the power 3. If you roll n number of dice, then the total number of possibilities will be 6 to the power n. If you similarly move, the total number of possibilities will be 6 to the power n. It is an equivalent number of outcomes of drawing r object from a total n object. So that firstly the object, again I am repeating same thing. It is an equivalent number of outcomes for drawing r objects from a total of n objects, such that firstly the objects are replaced after every peak, and secondly the order in which the objects are drawn does not matter, is given the following expression. So in this case, the number of permutations will be n to the power r. Again I am repeating. So here the number of outcomes or the number of sample space or the number of results for drawing r objects, you have to draw r objects where n number of total objects will be there inside the box. Inside the box there will be n number of total objects. So from n number of total objects, we have to find out the probabilities to draw r number of objects. So the probability can be obtained. The number of permutations will be n to the power r. And the experiment of tossing of 2 coins, we have considered certain values ht and th are equivalent. That is, the order of choosing the variable of object does not affect the total outcomes. Now coming to permutation. Let us now count the total number of outcomes when the order of choosing the objects does not affect the total number of possible outcomes with help of some example. So here we will consider example number 3.2. Consider a box containing 4 different balls. So inside the box we will find 4 different balls A, B, C and D. Calculate the number of possible ways of randomly selecting 4 original 4 original balls out of the ball without replacement. Again, I am repeating the question. So these are very fundamental things. Consider a ball containing 4 different balls. Consider a box containing 4 different balls. So inside a box, there will be 4 different balls, and the 4 different balls are labeled as A, B, C, and D. Now calculate the number of possible ways of randomly selecting the 4 original balls out of the box without replacement. So the first ball chosen can any one of the 4 variables, and for second pick we can any one of the 3 balls, and for the third pick we will have any one of the 2 possibilities, and for the fourth pick there is only one possibility. Hence the total number of ways for sequential but independent, hence the total number of ways that the 4 sequential but independent choices can be made must be 4 into 3 into 2 into 1, that is equals to 24. That means these 24 possible ways of randomly selecting the 4 original balls are the number of possible arrangements or permutations in any single sequence of the 4 balls A, B, C, D. You may note that if the balls are not leveled, in the previous case what we have discussed, the balls were labeled as A, B, C, D, but in the next case, if the balls are not leveled, these are indistinguishable, then 24 possible arrangements of discussed above will be referred to one combination. So that is only a single collection of combination of the 4 balls will exist. Also, if you choose to disregard the ordering of the picking of the balls, then the event, if the balls are labeled, we will have only one combination. Now let us take another example. So in this example, calculate the number of possible unique 9-digit numbers. Again, I am repeating the example. Calculate the number of possible unique 9-digit numbers that can be formed by using the digits 1 to 9 just once in a number. So that means 9 digits are there, 1 to 9. Out of the 1 to 9 digits, you have to use only one digits, right? 9 digit that can be formed by using digits 1 to 9. Just so you have to form a 9-digit number, and you have to use, for a particular number you have to use only once. While writing the desired number, there are 9 choices available for the first digit. For the second digit, the number of choices available is 8. For the third digit, the number of choices available equal to 7. And similarly for the next one, that is 6, 5, 4, 3, 2 and 1. So the total number of possibilities of getting a unique 9-digit number will be equals to 36, 3,62,880. So that is the 9 factorial. So each number in the example 3.3. So here we have discussed example 3.3. Each number is made up of unique arrangement of the numbers, that is known as permutation of the 9 numbers. Thus, from this experiment, we say that the permutation is a unique arrangement of all the available objects in which the order of selection affect the arrangement. In such type of permutation, all available objects are used in the arrangement, and the number of permutations of drawing n objects out of a set of n objects will be n factorial, that is the number of permutations will be written as np or pn. And here we will discuss another example. So in this example, how many 5-letter codes in English? How many 5-letter codes in English alphabet can be written which no letter is repeated? So you have to form a you have to form a 5 letter code, and each letter will be picked from the 26 alphabetical letters. So you have to form a 5 letter code. So for the first digit, there is a possibility the number of ways is 26 because 26 English alphabets are there. Now, after filling the first digit, for the second digit, the number of possibility will be 24 because already the first digit is permanent now. And similarly, for the third digit, the number of possibility will be 23, 24. Similarly, for the fourth one, the number of possibility will be 23. Similarly, for first one, the number of possibility will be 22. And the total number of possible arrangements will become P, that is equals to 7, 78 lakh 93,600. So thus, there are such a large number of unique 5 letter codes that can be created by using 26 letters of alphabet. So in this experiment, in this example number 3.4, we can see that represent the permutation of objects in which out of the all available objects, so the number of available object n equals to 26. Any subset, that is r equals to 5, is used in the arrangement. So the expression obtained in the example 3.3 can be written in terms of n and r. So for example 3.3, the expression can be written as, so this the expression can be written as P, or the probability equals to n into n minus 1 into n minus 2 into n minus 3 and so on into n minus r1, n minus r plus 1. This is the general expression for the possibility numbers of permutations of r object out of a set of n objects. It is represented by npr or pn comma r. So npr will be equals to n whole into n minus 1 whole into n minus 2 up to dot dot whole into n minus r and then n minus r plus 1. So in this equation 7, so the numerator in this equation 7 will become n factorial. Thus the total number of permutations choosing r object from the n object without repetition is given by this equation. If there will be no repetition, then the equation will be changed from this to this value. This refers to number of permutations of n object taken r at a time. You may note that when r equals to n, then the denominator will become 0 factorial, which is equals to 1. Therefore, the number of permutations will be n factorial. However, if the repetition of the object is allowed, then for every object to be chosen, all the n objects are available. Thus, the number of permutation for taking r object from the n object. So it is the permutation of taking r object from n objects. So that means in the box n objects are there, and we have to remove or take r object out of the n object, and the permutation will be n to the power r. Similarly, the number of permutations of getting n object where r1 object are one kind and r2 object are another kind. So the rk of the kth object is given by the expression, so that can be calculated by n factorial divided by r1 factorial into r2 factorial into r3 factorial and so on rk factorial. So the proof for this experiment can be had from any basic book of statistics. Now coming to configuration. There are certain conditions in which the order of choosing the object is not important. For example, if you want to select two books out of the three available books, A, capital A, comma capital B, comma capital C. Then you can select the book of the following ways. You can select either AB, you can select or AC, or you can select BC. So in this case, whenever you choose A first and B second, then choose B first and A second have the same set of books. So if you want to choose A first and B second, and in the other condition B first and A second, so in that case, if you want to select two books out of the three available books A, comma B and C, then you can select the number of books in the following way: AB, comma AC or BC. In this case, whether you will choose A first, then B, or choose B first, then A, you have the same set of books. Therefore, the order of choosing the object does not affect the outcome. You have three different combination of the two books out of the three books. When the order of arrangement, the objects are not important, then the collection of R object, then the collection of, again I am repeating here, in case whenever you will choose A first and B second, and after that you will choose then A, then you have the same set of books. So if you choose B first, A second, you will pick from same set of books, and if you choose A first, B second, you have to also choose from the same set of reference book. You have three different combinations. Two does not affect the outcome. So here three different combinations are there. Out of the three different combinations, two critical combina- two critical combinations are there. So you have three different combinations of the two books out of the three books. When the order of arranging the object is not important, then the collection of R object out of the N object is known as combination or configuration. Therefore, configuration is an unordered arrangement of R object out of the N object. So it is an unordered arrangement. That means automatically you have to arrange. Unordered arrangement of Therefore, configuration is an unordered arrangement of R object out of the N object. So the key difference between a permutation and combination is that the order of the element in the combination does not matter, whereas it does not show in case of permutation. In the simple word, there is no first place, second place, and so on. In case of combination, the combination of PQRS or PRSQ are identical and are not counted twice, whereas these represent to be one permutation of the alphabet PQRS. Thus, the number of combinations the number of combinations represents all the different subsets containing R items that can be sampled from N distinct objects. So here, for the specific arrangement of R object within the subset of irrelevant, and the number of combinations that can be obtained by dividing the number of permutations P and R. So by the number of permutations of the R distinct objects, that is the number of combinations equals to the number of permutations of R object selected out of the total capital N object divided by number of permutations of the selected R object. Mathematically, the number of combinations will be equals to NPR divided by R factorial, and here you will here substituting, so the number of combinations will be NPR divided by R factorial, and substituting for NPR we can get CNR, that is combination NCR, equals to NPR divided by R factorial, which is equals to N factorial divided by R factorial whole into N minus R factorial. So here one particular example is there. In this example, we will discuss calculate the number of permutations and configurations possible while selecting 3 balls out of the 5 different balls taken in a box. So here n equals to 5, r equals to 3, then the total number of permutations will be permutation of 5 to 3. So you can write like this. So if we'll remove its graph, so the number of permutations will be 5p3. So that is equals to 5 factorial divided by 5 minus 3 factorial, which is equals to 5 factorial by 2 factorial. And here the value of the 5 factorial you have to put, and here otherwise to solve in the denominator we will find 2 factorial, and here you will stop at 2 factorial, and that will be cancelled out, and the result will be 5 into 4 into 3, that is 60. So this is the number of permutations or the number of outcomes. So the total number of configurations, if we will calculate the total number of configurations, that will be 563, which is equals to 5 factorial by 3 factorial whole into 5 minus 3 factorial, which is equals to 5 factorial by 3 factorial into 2 factorial, which is equals to 10. So the number of permutations is 60, whereas the configuration is just 10. So this implies that for each configuration there can be more than one permutation possible. The expressions for number of possible outcomes for picking R object out of the total N object under different conditions as discussed here. So if the replacement is no, and that is ordered N, so this is the expression. So these are the expressions for number of possible outcomes for picking up R object out of the total N object. So total N object will be there, here we will picking R object. So if no replacement will be there, so all the objects are ordered in a particular geometrical arrangement, then the expression will be, then permutation expression will be applicable, and that will be npr, which is equals to n factorial divided by n minus r factorial. And if there will be no replacement, if there will be no replacement and it is not ordered, then the expression will changes into combination, and this is its value. And if both the cases will be yes, then nr equals to n to the power r is the expression of number of spaces of getting 4 number of items from 6 number of items. N number of items from r number of items. So these are the other examples. Here we have considered the situation for picking up certain number of objects out of a given total number of different conditions. Now let us now take up the examples of distribution of object. So actually here we will stop for 2-3 minutes, and after that again we will continue. So now we'll continue. Here we have so far considered the situations are picking up a certain number of objects out of a given total number of different conditions. That means up to now what we have discussed, the condition is, the situation is picking up a certain number of objects out of a total number of given out of a total number of objects under different conditions. Picking up a certain number of objects out of a total number of objects at a objects under different conditions. Now let us make up an example of distributing object with or without restriction. So in this example, so we are moving to the next step. So let us take three identical boxes and are considered the distribution of a red color ball among them. So three identical boxes are there, and the task is we have to so we have to distribute red color balls among them. We know that it can be accomplished in three different ways. So the first way is the ball is either first, second, or third box. Now, if we take the two identical red balls, we know that it can be accomplished by three different ways that is showing in this figure. The balls is either on the first or second or the third box. Now, if we will take two identical red balls and try to distribute them into three identical boxes, then the condition of each boxes can have only one ball. We find again there will be three possibilities as shown in the figure. So in the first figure shows that we will have three different balls. So in the first condition is that three identical boxes are there, and we have to distribute red color balls among them. So so the total number of ways will be there. You will put the ball. However, we'll take the so here so this is the first situation. Again, I am telling the first situation in the figure 3.1a. The ball is either in the first box or in the second box or in the third box, and hence the number of ways will be three. The ball may be in the, so that means you have to put one ball in three different identical boxes, and here we are calculating the possible ways of distributing the ball or the single ball in three different identical boxes. So that may be you may, so there is a first chance is you may put the ball in the first box, or the second chance is you may put the ball in the second box, and in the third one is you may put the ball in the third box. So there will be three different ways of distributing one ball. And in the second figure deals with that. The condition is you have to distribute two different balls in three identical boxes, and the condition is that two balls in a particular box is not allowed. This situation is not allowed. That means you have to keep two balls in two different boxes. And what is the possible number of weight? So the possible number of weights in the second case is also three. Why that is three? Here you two balls you have to put in two boxes. So the first condition is one ball in box one and the second ball in box two. The second condition is first ball in box one and second ball in box two. The third condition is the first ball in box two and second ball in box three. So here also you have to arrange in three different ways because these balls are identical balls. However, if you take a red and a blue ball, so now we'll move to slightly complex situation. So if you will take one red and one ball, out of the two identical balls, let us consider that one ball will be red ball and another will be blue ball, and distribute among the three boxes again with the condition that each box can have only one ball. We find out now there will be six possible ways of doing so that example. So these are the six possible ways. So the first possible way, in the first possible way, we have to keep the red ball on box 1 and blue ball on box 2. The second possible way, red ball on box 1 and blue ball in box 3. The third possible way, blue ball in box 1, red ball in box 2. Fourth possible way, red ball in box 2, blue ball in box 3. And similarly, so these are the fifth and sixth possible ways. We can say that when you say that when distinguishable objects are distributed into separate subsystems, there are more possible ways doing as compared to indistinguishable objects. So here the balls are two types, so that's why that is indistinguishable. Indistinguishable, one is red color and another in blue color. Now let us consider one example. Calculate the number of ways in which the three balls of different color can be distributed. Again I am repeating. Calculate the number of ways in which three balls of different colors can be distributed among four identical, that means four identical boxes are there. You have to arrange three balls of different color, not a same color, without any restriction. No restriction will be there. And what is the number of ways? And the second question is calculate the number of ways if you put a condition that box 1 can have only one ball and box 2 can have two balls, whereas the third and fourth boxes have no balls at all. Now in the first condition, let us label the balls are the red ball to be R, the blue ball to be B, and the green ball to be G. So the ball R can be placed in any one of the four boxes. And for each of these, the ball B can also be placed in any one of the four boxes. Thus, the number of ways will be 16. Again, each of again for each of these, there is four ways of replacing box. So the total number of ways is 64. And in the second example, so in the second case, calculate the number of ways if we put a condition that box 1 can have only one ball, box 2 can have two balls. So the condition is like this: box 1 red, box 2 blue and green. In second condition, box 1 green, box 2 red and blue. Third condition, box 1 blue. The second condition is block 2 box. The second condition is red and green. So in general, when total n distinguishable objects are distributed in k boxes such that n1, n2, n3 and so on, nk objects are there, then according to the combination of mathematics, the number of ways of w is given by the following expression: w equals to n factorial divided by n1 factorial into n2 factorial into n3 factorial and so on up to nk factorial. So if in the present case you have to n equals to 3, n1 equals to 1 and n2 equals to 2, n3 equals to 0, n4 equals to 0. So w equals to 3 factorial divided by 1 fact. So w equals to 3 factorial divided by 1 factorial into 2 factorial into 0 factorial into 0 factorial. Now coming to one very important approximation, that is called Stirling approximation. This is one type of long question. So that is called Stirling approximation. So we know that the factorial of n is defined as, so that means n factorial equals to what? N into n minus 1 into n minus 2 into n minus 3 and so on up to 3 into 2 into 1, etc. So this is n factorial. Now, so that thing we already known from our school level. N factorial equals to n into n minus 1 into n minus 2 into n minus 3 and so on into 3 into 2 into 1. So this is n factorial. Now taking logarithm of the above expression of n factorial, we can simply write ln n factorial equals to ln whole into ln n factorial equals to ln, because we are taking logarithm both side, ln n into n minus 1 into n minus 2 into n minus 3 up to dot dot 3 into 2 into 1, which is equals to, so here we are solving the RHS, which is equals to ln n ln n minus 1 ln n minus 2 ln n minus 3 plus dot dot ln 3 ln 2 ln 1. We can write the expression as a summation terms in the here ln n factorial equals to summation of ln n, where n started from 1 to n. Since n is a very large, accommodation can be replaced the integration within the limit. Therefore, since n is very large, summation can be replaced by integration with the limit. Therefore, we can write ln n factorial. So solving that one, we can just write ln n factorial equals to integration of ln n dn, which is equals to n ln n minus n starting from 1 to n. So the limit will be 1 to n. And here the value will become n ln n minus n minus 1 ln 1 minus 1, and finally you can get the result n ln n minus n. Thus, according to the Stirling approximation, ln n factorial equals to n ln n minus n. So this is about the Stirling's approximation. Now coming to the probability distribution functions. So here we will discuss the probability distribution functions. Where an experiment is carried out, there are different possible outcomes. Each outcome has some probability of occurrence. To characterize a random variable, we first need to we, we first need the information about all the characteristics of a random variable. Information about the possible outcomes of the elementary events of the random variable, and then get the probability of a given value as a possible outcome. Then recall that the case of tossing a coin having twice probability, there were four possible outcomes. If we could calculate the probability of getting a particular outcome, the probability distribution refers to revariation. So refers to the variation of probability of occurrence of all the outcomes in the experiment. Now let us recall the experiments given in above, in which the two dice are rolled simultaneously and the maximum value of some of the numbers on the top faces of the two dice the minimum value of sum of the numbers of the top faces of the two dice will be 1 plus 1, that is 2, and the maximum values of sum of the maximum values of the sum will be equals to n plus n plus 1. So here in this experiment, two dice are rolled simultaneously. The minimum number of values of sum of numbers on the top faces of the two dice is 1 plus 1 2, and the maximum values of the sum is around 6 plus 6, that is 12. So here the number of permutations and probabilities of different outcomes of rolling of dice. So the permutation to get, so this is the symbol represent, so here it is given the permutation. So these are the outcomes of rolling of dice. So this is the permutations. So the sum of the top face will become 2, then the permutation will be 1.1. Similarly, if the sum should be 3, permutations will be 2 1 or 1 2. That means if you add all the probability, that will become 3. So here the summation will be 3, and here the permutations will be 2 1 1 2, and the number of permutations are given here. In this case, the possible outcomes for two dice are 6 each and are independent upon one another. Then, according to the fundamental counting principle given above, already we have discussed, the total number of possible outcomes, that is the number of permutations, will be 6 to the power 2 or 6 square. So the last column of the table gives the probability of each of the possible set, the probability of each of the set of the each possible set of permutations of that sum. So the number of the top faces of the dice, you can clearly see that the probability depending upon the outcome, and here a plot, that is a variation of probability against the outcome, is referred as probability distribution curve or simply probability distribution. So the probability distribution is generally expressed in terms of mathematical functions such as outcome, that is the variable of interest. If x is the variable of interest, then the probability of distribution function is written as px. For specific outcome, the function is written. For the specific outcome, the function is written as px. In this above experiment, the variation of in the above experiment, the variable of interest is the sum of the digits on the top face of the two dice with discrete values 2 to 12. So these are the probability distribution curve. Probability distribution curve. Now, since the outcome of this experiment of discrete values of the probability distribution curve, that is called discrete probability or distribution function. In such a case, the total number of possible arrangements can be obtained by adding the values represented by bars in the histogram. So here the total number of values. So just wait for 2-3 minutes. So the probability of a variable having given value fi, the sample space is defined as pxi. So here the sample space is fi, and here the probability is pxi equals to fi divided by summation of fi I from I equals to 1 to n. The average value of the function is equals to sum of the values of the functions of all the function for all the values of x multiplied by probability of the variation with the corresponding value. So this is the average value of x. However, when the number of possibilities increases, it becomes increasingly difficult and the time consuming process to count the possible number of permutations, and after a certain stage it becomes impossible to determine the total number of possibilities by adding the possible permutations for each outcome. In such cases where the possible outcomes do not form a discrete set but continuum in R, then the distribution of the probability can be expressed by a smooth function that is called continuous probability distribution function. Then the total number of possible arrangements in such cases equals to the area under the curve. This can be determined by suitably integrating the probability function. The probability density function, the probability of an outcome for a small range of outcomes dx is given by the expression px dx. Here px is the probability density and represents the probability of an outcome to have the values between x to x plus dx. So the total probability range is given by the integration of px dx from x1 to x2, and the probability distributions are usually normalized. It implies that this condition will be satisfied according to the quantum mechanics. So the normalized function. So this is the condition of normalized function. So this condition means integration of px dx equals to 1. Integration of p square dx. So here one printing mistake is there. You have to write p square dx. So here p square dx. The probability of a variable having the given values f of x in a range of x is defined as this, and similarly the probability can be used to determine the average values of some variable. Let us consider the variable x that can have certain possible individual values. So it will have certain possible individual values. Then if the certain possible individual values will be xi, we represent the probability that a given value xi exists as pi, and here the average value of the variable will be represented by this. So these are some questions. Calculate the number of permutations and configurations possible, selecting 3 toys out of the 4 different toys labeled as A, B, C, D. So already this type of question we have solved. Identify the explicitly each combination and permutation for the 3 chosen toys. Now coming to the terminal questions. So the terminal questions you have to solve. What is the probability of selecting a card of spade from a standard deck of 52 playing cards? So that means it is not given which color spade, you have to just spade. What are normalized variables? Name their types. And consider an unbiased coin is tossing thrice. List all the possible outcomes and calculate the probability of getting head exactly twice and getting tails at least one. So these are the questions you have to solve that one. Very interesting questions. So in this unit we have just discussed very fundamental statistical concepts like permutations, combination, probability, etc. Now, in the second module, in the second unit, or that is overall the fourth unit, in the second unit, here we will discuss same introduction of statistical thermodynamics, but here we will discuss about the Boltzmann's distribution, molecular partition function, canonical assembly, thermodynamic properties from partition function, average energy of the molecules. So all these things we will discuss in this unit number 4. So here the first one is Boltzmann's distribution. Okay, better we'll continue this unit on tomorrow's class. So that will be better. So we'll continue this unit in tomorrow's class. Okay.